Alrighty, we are live. This is the first 1026 quiz session, weekly review session, study session, whatever you want to call it. Let me go ahead and pull up this word stuff here and do a new one. I'm going to say 1026 review session starts at 4 o'clock. As of right now, I'm going to try 4 o'clock on Sundays for these 1026 sessions. To access them each week, basically all you need to do is click the join button and click on the weekly study sessions option. And I'll be doing these just for members only each week, but this first one will be free for anyone to watch who might need help on their quiz 2 stuff. I think y'all have to take this by Tuesday, if I'm not mistaken. Let me go ahead and set this up. Get rid of that. Once I pull this up, I'm going to go to the bathroom before we start. And we'll get started in just a few minutes. All right, not bad. Well, let's pull that over. We'll just do that. That's fine. All right, I'll be right back. Alright, what's it looking like in here? Where's that thing? There we go. Alright, what can we see here? We got the candle. Yeah, we got the vibes. What light we going for today? What's the vibes we got? Got red. Got the LEDs. We got the upgrade. That looks. Is that bad? That's stupid, isn't it? Let's go orange. Yeah, just like these like warm yellowish lights. They just look dumb on camera. Come on. That just looks too dark. Go extra bright. A little too bright. Oh. Man, that's vibes too. Purple. I like the purple. Don't really look purple on there. Man, my face looks all sorts of yellow. That's probably not what we're going for. That's probably from this thing though. I got like a ring light too. Alright, it's 4 o'clock. Let's probably get started here. Let's go ahead and start. So, welcome to the first 1026 weekly review session. We're gonna try this out. We're gonna do this one, free for anyone to watch. And then if you want to continue watching these each week, just hit the join button and click on the weekly study sessions option. Alright, let's get into it. Today, we're going to be covering the topics: directly versus inversely proportional, fixed law, predator-prey models, and the SIR model. And basically all I've pulled up are some practice problems that you could possibly see on your quiz 2. There might be like 10 to 15 problems, might be multiple versions of the same type of problem. Kind of some of the harder problems typically, kind of just working through them and giving you some tidbits of advice along the way. And that's probably what these like sessions will typically look like. Also, as we're going through the weeks, hopefully more people get involved with these live sessions. That like it will encourage you to send problems that you're having trouble with, so I can work them out during these sessions, right? So ideally you can send me the problems before the session each week, and I can work them out during the session. So let's go ahead and jump into it. We'll call this problem 1. Problem 1, they say use the information to create a mathematical model that incorporates all variables, and then find k, and then that's pretty much it. All right. So they start off by telling us that n is inversely proportional to the square root of m. So to say that n is means that n will be equal to, and it says n is inversely proportional to the square root of m. Now right away, anytime you see the word inversely proportional or the phrase inversely proportional, inversely means that the thing they're talking about, in this case the square root of m, will go in the denominator of the opposite side of this equation. So we want to see the square root of m in the denominator of what is basically n. So n is inversely proportional to the square root of m. That's it. And then that same n is proportional to the square of q. So to be just regularly proportional, or typically it's called directly proportional, what that means is the square of q should be in the numerator of what we're talking about, or the numerator in this case of n. And something we're missing, for each of these there's typically a constant. So whether it's the first statement or the second statement, you typically will see a k. You could say it's in the numerator, or if we had wanted to, we could have put it just on the outside here. Anyway, we have k times q over square root of m. Then they give us some values. They say n is equal to 2.8, square root of m is 0.2, and the square of q is 1.6. So all we're going to do is plug in these given values, and that will be enough to solve for k. So right away, they say n is 2.8. So we're going to say 2.8 equals k, which we do not know, but they tell us that the q should have a square on it from the start. They said square of q, so that's q squared. So they say the okay, so the square of q is 1.6, so q squared is 1.6. Then kind of jumping around here, the square root of m is 0.2. So not just m is 0.2, but like just straight up the square root of m is 0.2. So we don't have to worry about like the square root or the square, because they're giving us those values q squared and square root of m, right? All right, so now we can maybe simplify this and then move it to the other side to solve for k, or get k by itself. So if we take 1.6 and divide it by 0.2, it's almost like 16 divided by 2, which is 8. and then we still have 2.8 on this side, so we have k times 8 over here. So to get k by itself, we're going to divide by 8, canceling that 8. So we have 2.8 divided by 8, which is, let me use my phone real quick. We have 0.35, so 0.35 should be equal to k. And that's it. So a little bit of insight on proportional versus inversely proportional and solving for k, and yeah, that's pretty much it. All right, let's go on to problem 2. They say consider the mathematical model for Fick's law, and then they ask 3 statements. Okay, so Fick's law, let's kind of write out what that sort of looks like here. Fick's law is what's known as a differential equation. It's the rate of change of the, it's the rate of diffusion of something in a cell, or maybe just diffusion of the cell, something along those lines. So it's the rate of change over time of diffusion. And so what it should look like, there's a k, there's an area, so a surface area typically, in a numerator, being divided by the thickness of the cell. How do they word that here? Do they just say thickness, thickness of the cell's membrane, like you can see there. So I'll just call it thickness. And then it's multiplied by the concentration, it's like the change in concentration. And the change of concentration you might see represented in sort of a shorthand known as delta C. So delta representing like the change in, and C representing concentration. So given this differential equation, we are to kind of analyze how the rate of diffusion will increase or decrease if we change certain parts of this right side of the equation here. So let's jump right into it. We'll kind of learn as we go here. Teach as we go here. So number 1, they say they're analyzing Fick's law. They determine that if a surface area, a cell's surface area increases, then the rate of diffusion increases. So for the surface area to increase, that means this surface area value that is in the numerator is being increased, or it's increasing, and they're asking how will this affect the rate of diffusion. Again, this left side, this dN over dt, is the rate of diffusion. And so if we increase the surface area, which is right here, then because it's in the numerator, then the rate of diffusion will also increase. It has that direct proportion, relationship, directly proportional relationship. So that is a true statement. Because surface area is in the numerator, it will have like the same effect on the rate of diffusion. Now, let's go to the next one. They say, number 2, if the change in concentration, again, which is right here, if the change in concentration increases, then the rate of diffusion will decrease. Well, change of concentration is technically in a numerator, right? It's kind of like divided by 1. The biggest thing is that it's not in a denominator, right? So if that's increasing, if change in concentration increases, then the rate of diffusion should also increase, but they're saying that it decreases. So that must be false. Number 3, they say a researcher notices, researchers notice the area of the cell increases, in other words, the surface area increases and the thickness of the cell's membrane increases. They determine the rate of diffusion must increase. Now, here's the weird thing. If the surface area is increasing, and it's in the numerator, and the thickness is increasing, and that is in the denominator, well, because we don't know by how much each of them are increasing, we really can't say what's going to happen to the rate of diffusion, because they could be increasing at the same amount by like similar amounts or different amounts. Like, we just really don't know what's going to happen with this given information. Something to point out that didn't really come up in this case, if they had just said that the thickness was increased, if the thickness increases, that would have the inverse effect on the rate of diffusion. So let's go ahead and say 3 is false from what we said before about surface area and thickness. If they both increase, we don't know what's going to happen to rate of diffusion. But different scenario, if the thickness is increased, then the rate of diffusion would decrease, because the rate of diffusion is like inversely proportional to the thickness. They have an inverse relationship. If one goes up, the other goes down, and vice versa. Okay, so a little lesson there regarding inversely proportional. So in this case, we only said number 1 was true, so only 1 is correct here. All right, let's move on to what we'll call number 3. And I'm going to grab this fixed law from this one because it will apply to this next one. Let's try that again. All right. All right. How we doing? We got 2 viewers. Welcome to Practice Problem Videos. Oh, nice. You have all the reviews on 1025. Yes. So for 1025, I'll be doing those this semester as well. I don't currently have them, but I'll be doing them as we go through the semester. But I do have all the like practice problem videos. So like problems you'll see on your quizzes and exams. Yeah. All right. So let's keep it going here. Let me keep that chat visible. All right. Number 3. They say we have a researcher classifying cells, measuring the rate of diffusion, in other words, dN over dt. Okay. Order the following cells by increasing diffusion rates. So we basically just need to find or calculate dN over dt, the rate of diffusion, for each of these cells given. And they give us all the information to calculate the rate of diffusion. So we basically just need to do that for all 3 of these. So I'm going to demonstrate it with cell 1 by hand, and then I might do the other 2 on Excel just to show how you can, utilize Excel for a problem like this, which involves like a lot of plugging and chugging. So let's give it a shot. They say we have for cell 1 we have a K value. So I'm going to say cell 1. I'll say K is 4.14. They give us the surface area, which you can kind of see here. It's A times 10 to the negative 9. We can sort of ignore the 10 to the negative 9, and I'll tell you why in just a moment. So we'll just plug in place of the area, or the surface area, 5.61. And then in place of the M, that is actually the, what's that, in meters? So it's the thickness of the cell membrane, but it's meters times 10 to the negative 9, right? So it's like micrometers or one of those. I'm not sure. But in place of the thickness, we will plug in 5.03. And then here we see the delta C that I mentioned before. Delta C represents the change in concentration. So we can just plug in 2.94 right there. And that's it. So we're basically just calculating this value and seeing what we get. So I'm going to go ahead and just do this and then do the other 2 in Excel and kind of demonstrate those on the computer here. All right, thanks for bearing with me. So we're gonna do something like this. We're gonna do cell 1, cell 2, cell 3, and we're just gonna calculate the rate of diffusion right here. So we're gonna do surface area. I guess it would help if you were like given these charts. Yeah, I don't know. We'll still do the calculation here, but let's see if I can get it over there. Just bring it right here. All right, so we're just going to plug this in. 4.14 times 5.61 divided by 5.03, and then times 2.94. So I just need to make sure to have multiplication signs or asterisks in between where we're multiplying things. So basically I've just plugged in this right here. You can see it across the top here. We'll just hit enter and we'll get a value for that. Now we're basically doing the same thing for the remaining few options here. Now, something I didn't highlight was this. The reason we can ignore the 10 to the negative 9 here is this. we could have included times 10 to the negative 9 up top and times 10 to the negative 9 on the bottom here, right? But if we're dividing these two values, ultimately these 10 to the negative 9s will cancel out, so that's why we can sort of ignore those there. So now, for the following cells, we will do the same calculation. So I'll just kind of do that real quick here. We want the K. I wonder if I can get it visible there so you can actually see what we're doing. So we want the K value times the area, which is 4.33, and we're dividing by the thickness. So for cell 2, again, that's 7.96, and then we're multiplying by the change in concentration. For cell 2, that is 2.66. And then I forgot to hit the equals. Always start with the equal sign when you're calculating a value. And then we'll do the same thing for this last one. So K, 2.73 times the area, 6.78, divided by the thickness, 5.80, and then multiply by the delta C, change in concentration, 1.07. All right, and then they tell us to order them in increasing, put them in increasing order, so smallest to largest. So we have smallest, middle, largest. So cell 2, 3, then 1. Let's see if we can find that here. Cell 2 is less than cell 3 is less than cell 1. We're looking at option D. And that is our answer here. And that's pretty much all there is to it. All right, let's go on to the next one. I'm going to aim to get out of here by 5 o'clock. I think we're on all right pace here. That was number 3. Let's call this number 4. Take a little sip, take a little break. All right, kind of a similar problem, kind of different. Let's look into it. They say the model in these problems is just another word for equation, basically. So the model, in other words, this equation fits both samples below. So we have sample 1 and sample 2 with all these different values given. And they say, what is the missing data point? So because this model fits both samples, what that means is it's like consistent, or it works for sample 2's values and sample 1's values, meaning we can plug in all of sample 2's values in here, and we think about what's the only letter or unknown that we have here that we do not have here, right? So what I'm talking about is K. This letter K we do not have a value for. So the approach is to plug in the sample 2 values here, and we'll have everything to plug in except for K. So plugging in all those values will allow us to solve for K. Once we have K, we're going to use that K value with these 3 values for sample 1, and that will allow us to solve for the Z for sample 1, the missing data point. All right, let's get started. Starting with sample 2, we're plugging in everything we know into this equation. So sample 2's values, we have Q is 74.1. We have K, which we do not know. We have Z squared. Well, Z is 17, so we're going to square that. And then we're dividing that by L times M, which is 3 times 13. All right, let's go ahead and use Excel since we're right here. So we'll say, we'll just go ahead and calculate 17 squared. Make sure to do the equal sign. 17 squared divided by 3 times 13. We'll go ahead and put parentheses around that, like that. So we have 7.41. So 7.41 is what we have being multiplied by K here. So 7.41. And our goal is to solve for K. So we're going to take 74.1 and divide it by 7.41. Well, if you have a guess, this might be a good time to, this is not a bad one to get, right? It's 10. The answer is 10. You can probably see that, there's a nice little value there because of those numbers. We have a K value of 10. All right, so we have a K value of 10. Now we're going to use that with these sample 1 values and solve for Z in sample 1. So let's go ahead and set up the equation as far as we know. We're setting up this equation with the sample 1 values plus the Q value. So we'll say Q is 2. We know k is 10 now. We don't know z, but we know that z should be squared. Don't forget the squared. And then we have L times M on the bottom, so 5 times 16. And then here our goal is to solve for z, right? So we need to get z by itself. Let's kind of work some of this out by hand. I'm going to start by dividing by 10. That'll get rid of it there. We'll have 2 over 10, or 1 over 5 is equal to z squared over 5 times 16. If we want, let's go ahead and do 5 times 16 here. That is 80. So we have this. We can go ahead and multiply by 80 to the left side. It's almost like multiplying both sides by 80, I suppose. And when we do so, it'll basically take the place of the numerator that was previously a 1. So then we have 80 divided by 5. And 80 divided by 5, well, if we did 5 times 16 to get 80, then 80 divided by 5 must be 16. We have 16 equals z squared, and to get z by itself, we take the square root of both sides. So we have 4 is equal to z, and we're done. Because that's what we were looking for. We were looking for that missing data point of z of 4, I suppose. All right, that was number 4. Hopefully there are no questions. Hey, they got 2 people watching. That's fun. All right, thanks for tapping in. If you have any questions, let me know. All right, so we're getting into some of the predator-prey model ones. I went ahead and put all 3 versions that you might see for this specific problem on here, just so you get a highlight reel of each of these, right? So in this problem, there is a population of salmon, otters, and bears. Salmon are at the bottom of the food chain. Otters are kind of in the middle, and then bears feed on both otter and salmon. So let's kind of talk through it and teach it as we go here. In this first one, you'll notice, I'll just go ahead and say this, you'll notice across these different problems, they might ask you about S prime, O prime, or B prime, representing salmon, otters, and bears, respectively. So in this first one, they're asking about basically the rate of change of the salmon in this ecosystem, right? The rate of change of the salmon in this ecosystem. The salmon are at the bottom of the food chain. They do not prey on anyone in this food chain. They aren't eating. They're kind of just on there. They might be eating each other. I don't know. But they are not predators in any way. But they do have predators. They have otters and otters and bears. So basically what should happen, the relationship between the salmon, otters, and bears, the more otters there are, the less salmon there should be. It'll be a more negative effect on the salmon. Likewise, the more bears there are, the more negative effect there will be, or the less salmon there will be, right? So we need to find the differential equation, or the S prime equation, that kind of represents that. So what we're looking for is, in the S prime equation, we want to see B with a negative effect on the salmon population. We want to see the O with a negative effect on the salmon population. So B with a negative effect, O with a negative effect on the salmon. And then I think the salmon will just have a positive effect on the salmon. You don't need to worry as much about that though. So anyway, A is looking good. Let's go through the others and eliminate them and kind of talk more about it. Salmon prime equals B with a positive effect. So what this is saying right here is that the more bears there are, the more salmon there will be, which is not right. The more bears there are, the less salmon there will be. So you want a negative value right in front of that B term here. So B is off the table. And C, they have a negative next to the B, but they have a positive next to the O, which is saying that the otters have a positive effect on the salmon population. But they do not, because the otters are eating the salmon. So C is off the table. Let's look at this last one. It's saying the bears and the otters have positive effects on the salmon. That can't be right. So we're going to eliminate that. We're looking for one like A. And it'll be the case every time that you'll see like bears next to salmon, like it'll be B and then S, likewise O and then S. You'll never see just B by itself or O by itself like that. You'll want to see it next to the salmon, variable like that. All right, let's go on to otters. So again, otters are kind of in the middle of the food chain. So they eat the salmon, but they're also being eaten by the bears. So we want to see a situation. We want to find an equation here where the otters are basically like the bears have a negative effect on the otters, but the salmon have a positive effect on the otters because the otters are eating the salmon, right? So let's check it out. Otters here, we have the bears have a positive effect on the otters. That's not right. The bears are eating the otters. Let's eliminate that. Option B. We have bears have a negative effect on the otters. That looks good. We have the salmon having a negative effect on the otters. That's not right. They should have a positive effect on the otters. And then C, we have the bears having a negative effect on the otters. That's correct. And then we have the salmon having a positive effect. And that is correct too, because the more salmon there are, the more otter will be able to feed on the salmon, and the population will grow for the for the otters. Goodness, a lot of juggling stuff. So C will be our answer here. Let's go ahead and disprove option D. We have bears with the positive effect on the otters automatically. That's false. And the last scenario, we have bears. Rate of change of bears in this population. Again, bears are at the top. They're feeding on the otters and they're feeding on the salmon. So basically, the otters and salmon will both have a positive effect on the bear population. So we want to see positives, lots of positives. So like if we see negatives, let's get rid of them. So maybe not necessarily this negative, but we'll keep going through. Yeah, we're going to go ahead and get rid of option D here. So I kind of just did a quick scan. We see otters with a negative effect on bears. Let's get rid of that. Let's talk through both these here. So B, we have B prime. We have salmon with a positive effect on the bears. That looks good. We have otters with a positive effect on the bears. Now, what's missing from this? Usually, again, we should see the bears paired with the otters. Like we should see whatever population we're talking about with the, other species, right? So we do not see O with the B here. So I think that makes B false. And then this option C, we have otters having a positive effect. We have salmon having a positive effect. And then the bears have a negative effect on themselves, which actually makes sense because if there are more bears and all these bears are competing for all these, all this prey, then not all the bears can eat. And so the more bears there are, it'll have a negative effect on the bear population overall. So C is our best answer there. There's a good look at all three examples on one screen. Hope that makes some sense. All right, let's keep going. I don't even know what number that was. We'll call that 5 for all three of these. How we doing on time? About halfway. Let me see how many problems I got left. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, we got to pick up the pace here. Let's keep going. All right, this one. Jumping right into it, they give us X prime, Y prime, and Z prime, different populations, different species. And they ask which of the following are true. Number 1, they say species X is a predator of species Y, meaning X, eats species Y, preys on Y, which should mean that X should have a negative effect on Y. So, say we looked at the Y population, the Y prime, rate of change of Y. That means X should have a negative effect if they are the predators of Y. Well, as we see here, X with the Y, X has a positive effect on Y. And we don't see any other X's in this mix here. So right away, this is false. Another way we could check this is if X is a predator of Y, what that should mean for the X prime is that Y, the more Y there are, the more X there should be. In other words, the more y there are, y should have a positive effect on the x population, because the x should be feeding on y, right? And so when we look at this first equation, we see the y, but we see it has a negative effect, actually, on the x. And what that would mean is, I think it's just the opposite of what they're saying here. So instead of x being a predator of y, I think y is a predator of x. Again, because the more y there are, it's having a negative effect on the x population, meaning y must be feeding on x. Number 2, z is a predator of x. So to be a predator of x, again, z is a predator of x, so they'd be feeding on x. So sometimes it's hard for me to categorize these. So if z is a predator of x, they should be feeding on x, which means x should be negatively impacted by z. So if we scan through x, we should see some kind of z, right, with a negative value in front of it. But in fact, we don't see any relationship at all between x and z. So if you see z and x together like this, you can automatically eliminate that option. That will not be true. Number 3, species z is not a predator of x. That seems fair, because we just said that they don't have any relationship whatsoever. So that's got to be true. So we're looking at number 3 is correct. So D is our answer here. Hope that makes some sense on the predator-prey models. Yeah, let's keep rolling. Got some more predator-prey stuff here. Here they give us an H prime and an L prime, and they give us some sort of initial values is what we're calling them. So they're basically giving us pairs of T and H values and pairs of T and L values. So this first one here, they're saying when T is 0, H is 2. And the second one here, they're saying when T is 0, L is 2. So what we're going to do is just plug in these values, mainly just the H and the L values, into H prime and L prime. We're going to calculate H prime and L prime. Okay, so H prime, we have 7 times H. So H is just 2. So it's kind of important to think about it like this. Wherever they say H of T or L of T, it's really just another way of saying H or L. So you can almost ignore the of T. I wouldn't worry about it too much. So this is basically saying 7H minus 3HL for our H prime, right? So that's all we're calculating here. So we'll say 7 times 2 minus 3 times H, which is 2, times L, which is 2. Now we want L prime as well. So for L prime, again, we can get rid of these T's. So we have H times L, which is 2 times 2, coming from these values again. And then, let me fix this 2. These don't look like great 2's. All right, so we have 2 times 2, H times L, minus 5 times L. So 5 times 2. We're going to go ahead and calculate these real quick. We'll say that H prime up here is 7 times 2, which is 14, minus 6 times 2 is 12. So 14 minus 12 is 2. So H prime is 2. L prime we'll calculate below it. We have 4 minus 10, which is negative 6. All right, so we have H prime and L prime. Then what they ask is this. What would you expect regarding H at point 1 and L at point 1? So what this means is when the time is point 1, what will H be? More specifically, they're asking how will H at time point 1 compare to the H value at time 0? Will it be greater than or will it be less than? Likewise, at point 1, will the L value be greater than or less than the L value right at time 0? Okay, so what do we know? For times 0, we know that h was 2, and we know that h prime was also 2. The important thing about the h prime and the l prime is not so much their value, but if their value is positive or negative. So, in this case, h prime is positive. So when h prime is positive, what that means is over time, or as t gets larger, h should also increase. It should also get larger. So what that means is h should be greater than 2. Since h was 2 at time 0, then at point 1, h should be greater than 2 because the rate of change was positive. All right, let's do the next one. Right here, we see that L prime was negative, and so if L prime was negative, what that means is as time increases, then the L value should go down. So at time point 1, L should be less than whatever it was at time 0. So in this case, it should be less than 2. So what can we say here? We can compare these now. We can say that the h value at point 1 should be greater than the h value at 0 because it increased because of its positive rate of change. And then the L value at point 1 should be less than the L value at time 0 because the rate of change over time was negative. So we're looking for the answer with these two statements in it. And it looks like, I think it's option A. All right. Hope that makes some sense. Little insight on this stuff here. Let's keep it rolling. We're going to go to number 8. And in this problem, they say which of the following statements are correct, yada, yada. Okay, so they're talking about a specific predator-prey model where they have h primes and l primes. So you like do and don't have to memorize this. Like if we see this problem, you can actually kind of like come up with the model they're talking about by looking at this example here. So what I mean is the 7 and the 3 and then the coefficient here will be like our A, B, C, and D. And then this predator-prey model will just like have that structure in any of these problems. So let me write out what I mean. H prime will be A, we'll say A times H, and then minus B times H times L. So see how there's the parallel between this H prime and this H prime? There's like a times H minus B H times L, right? All right, let's keep going. That's kind of what we can use here. So L prime will be kind of, we'll use this as a guide again. We have H times L, which I will throw a C in front of. Hoping there's a C in these. Yeah. So we'll say C times H times L minus D, and I think it's just times L. Yeah. All right. And I'm hoping it's subtraction. Yeah, I think that should be the case. So these are the H prime and L prime equations or models we are using in this problem. So given these, let's answer these statements here. They say they determine that if parameter A decreases, keep in mind A is right here, then H prime decreases as well. Well, that must be true because if A goes down and A is, previously a positive value, there's no minus in front of it, it's just positive, right? If A goes down, then it's taking H prime down with it. So that is a true statement. Number 2, they say if the parameter D increases, so here we're looking at D, if that increases, then L prime will, oh sorry, I think I read that wrong. If parameter D increases, then L prime will also, L prime will decrease. So if D increases, L prime, I think what's confusing me is I was saying D increases and then I was saying decreases. So stupid. All right. So if D increases, then L prime will decrease. Could this be true? Well, if there's a subtraction sign in front of the thing that's being increased, then what's going to happen is you're going to be subtracting a larger value, which for the overall value of L prime should make it go down. so it is true. So if you increase something that is being subtracted, the overall value will decrease. Hope that makes some sense. This statement should be true. Let's go on to number 3. All right. They say if C increases, then L prime decreases. So if C increases, L prime decreases. That is false. So if C is increasing and C is already positive, we're not subtracting it from anything. It's only adding to the value of L prime. If C is going up, then it's bringing L prime up with it. So to say it decreases is false. So we're looking for 1 and 2 to be correct here. Hope that makes some sense. Again, you will use this model in any of these types of problems. All right. That was number 8. Going to number 9. Getting into some SIR model stuff. Let's see how we're doing on time. We got about 20 minutes, so that's what I'm aiming for. Got a few problems left. Okay, we're doing all right. Let's keep rolling. SIR model. In this problem, they give us this S prime, I prime, and R prime model, known as the SIR model. They give us S values and I values for specific times, and they say which of the following are true. So then we're comparing S prime and I prime, R prime and I prime. So basically all we need to do is, with these given S and I values, we are going to calculate S prime, I prime, and R prime, and then we're just going to compare them and see which of them, then we're going to compare them and see which of these statements are actually true. So I think I'm just going to do this in Excel. The way we're going to do this is, again, the S value given is the 753 right here, and the I value given is 864. We can sort of ignore the times 6 because that's all we're dealing with is times 6. We're not dealing with any other times, so we can just assume that we can just say S is 753 and I is 864. We're just going to plug these values in to all 3 of these and then kind of compare their values. So here, oh gosh, sorry. Here we can use Excel. So I will demonstrate using Excel for this one. I'm just going to pull it over here. We'll do it right here. We'll start at 10. We're going to calculate, I'm going to go ahead and label them actually, S prime, I prime, and R prime. Then right here we can see what I'm plugging in. We'll say equals. So we have negative point zero, what is that? 3 zeros, 1, 2, 3, and then a 5, and then I, so we'll do times I, which is 864, times S, which is 753. And that's it. We're just going to do this for all 3 of these. So then we can do point, so we do equals 0.0005, again, times I times S, so times 864 times S, which is 753. And then we're doing minus 0.2 times I, which is 864. And then the last one, just 0.2 times 864, or I. All right, so I'll click on each of these. You can kind of scan through across the top here how I calculated each of them. Again, these all just came from this SIR equations here, these SIR equations. All right, let's compare these. So we have S prime, I prime, and R prime right here. They say, number 1, S prime is greater than I prime. Is S prime greater than I prime? In absolute value, it is, but it has a negative in front of it, so technically that negative would make it less than I prime, which is 152. So number 1 looks false. And number 2, they say R prime is greater than I prime. Well, R prime is 172, and they're saying that's greater than 152. That checks out. So number 2 is true. So we see only 2 is correct. And that's all there is to it. It's not too bad. Hope that makes some sense. Let's keep rolling. We're going to do number 10. Oh gosh. All right. I'm going to take a little water break. All right. All right. Let's jump right into it. They say, suppose a town of this many people is experiencing a viral outbreak. On day 11, 290 people have been infected, and an additional 41 become newly infected that day. What's known about the virus? They say it takes 25 days for a person to recover, and then that person becomes immune. What are the correct SIR model parameters for this situation? Now, the A and B, what the heck are A and B? Well, if you look back at this one, you might have noticed that there was kind of an overlap, like this 0.0005 showed up in this equation, but it also showed up here. Likewise, the 0.2 showed up here, but also in the next one, right down there. And so these values, the 0.0005 is the A value, and the 0.2 in this case is the B value. So we can kind of gain from that the general form of the SIR model, okay? So we can say that if we wanted to, set them up, we don't need to set up the entire thing for this one, but I'll just do it real quick just so you have it. So we have S prime is negative A S times I, and then we have I prime is A times S times I minus B times I, and then we have R prime is just positive B times I. All right, and so what do we need? What do we need to know? B is found by doing 1 divided by the days it takes to recover. So that's usually the first thing I calculate because it's the easiest, and we need it to calculate A. So they tell us it takes 25 days for a person to recover, and so B is 1 over 25, which as a decimal, if we divided that, we would get 0.04. So right away we can eliminate this option that has the crazy decimals and narrow it down to either C or D. And then what we're going to do is use the one equation from the SIR model that actually relates both A and B, and that is I prime. So given the I prime up here, we are going to plug in values that we are given to calculate the value of A. Now, there's kind of a twist with this one, but I'll point that out in just a moment. They tell us on day 11, 290 people have been infected. In other words, the number of infected is 290. Again, don't be confused by like the day 11 and then the 290. It looks like 11,290, right? But it's just saying the infected is 290. And then what else do we know? We know that 41 became newly infected that day. What that means is they're trying to hint at the rate of change of rate of change of the infected is growing at 41 per day on day 11. Okay, so I prime is 41, and then that might just be it. Oh wait, actually, sorry. We need the susceptible. Stupid. So we need the susceptible, which is the S, and the susceptible comes from the total number of people minus the number of people who have been infected. And so we take 142,290 minus 290. Naturally, taking away the 290 leaves us with 3 zeros on the end. They always do that, for our benefit there, so that we just are left with, the value in hundreds, thousands, 100,000s. Yeah. And the reason we only need to subtract the infected from the total number of people is this. Typically, we would take the total number of people and subtract not just the infected, but also the people who have recovered. Because if you've recovered and you can't catch the disease afterwards, then you are no longer susceptible. But the issue is we're only on day 11 in this problem, and it takes 25 days for you to recover. So really on day 11, no one has recovered yet, so we don't need to subtract any recovered from the total. All right, getting a little too deep into it, but I hope that makes some sense. Now, here's the extra twist that I mentioned earlier. In this equation, I think it only works if you take off this I right here. Can't explain why. It's just something I had to find using trial and error over the years. So let's plug in the values into this, and our goal is to solve for A. So we'll say I prime is 41. We don't know A, but we know S is 142,000. We know I is 290. We know B is 0.04. And that's it. And so let's go ahead and add the B value to the other side. We're going to call it 41.04. We'll have A times whatever this product is here. I'm just going to do that on my phone real quick. Call it 142,000 times 290. We get 41,180,000. Yeah. And then we solve for A by dividing by that value we just got on both sides. So we have 41.04 divided by 4,1,180,000. All right. And I got point. This is fun. We'll say probably was a bad idea to do it on my phone, but what I have is 5 zeros, then a 1. And what that is this answer rounded up. I'm going to do this in Excel real quick. Hold up. Just that very last calculation. Just because that's a stupid answer I just got. I'm going to do 41.04 divided by 41,180,000. There it is. That looks a little nicer, right? So we get, exactly 9.96 e to the negative 7, which is another way of saying times 10 to the negative 7. So that's how we find option D as our answer. So I'll just say A is equal to, just write it how Excel had it here, 9.96 times 10 to the negative 7, more or less. All right. And that's all there is to it. So again, I was only including this because it might be helpful to know the SIR model, but otherwise, again, we just use basically the I prime, the modified I prime. Again, we left the I off the end like we would typically have. B is 1/days to recover, and then we plug everything we know into this to solve for A. All right, let's go on to what we'll call number 11. Let's check it out. I think I have 2 versions of this one. Yeah, just to show you different examples. They say, suppose a town of, let's get back to this. All right. Suppose a town of 28,000 people is experiencing an outbreak. Once individuals recovered, they are resistant to the virus. That is very important in these problems because it'll mean there will be a number of resistant people. In other words, R will be a non-zero number. It won't be 0. It'll be a non-zero number. So one of these guys, right? They say at time 10,080 people are ill or infected, and 5,880 other people have been ill and recovered. So they're straight up telling us that the recovered number of people is 5,880. So right away, we can narrow it down to these 2 options. We're going to eliminate all these. So we're between D and E. Then they say, if S represents the susceptible individuals and R represents the resistant individuals, what values would be assigned to S10 and R10? So again, we briefly mentioned this in the last one, I think, about the number of people who are susceptible. For the number of susceptible individuals, we take the total and we subtract the infected and we subtract the recovered, or I guess the now resistant individuals. So I'll say res. So total minus infected minus resistant, because that just leaves the number of people who have not gotten the disease and who have not recovered, the susceptible, right? So we take the total given, so total number of people is the town of 28,000 minus the infected, the ill people, that is 10,080, minus the resistant, which is 5,880. So just briefly in my calculator, we'll do 28,000 minus 10,080 minus 5880, and we get about 12,040. So I'm looking at option D, and that should be it. All right, not too bad, right? How about a second version? We're going to call this 11.5. What's the difference? They say, suppose a town of 26,000 people is experiencing an outbreak of 2 different diseases. That's pretty cool. Not cool, but it's different, all right? Individuals can be infected multiple times with either disease immediately after getting better. Wow. That sucks, right? All right, so what does that mean? They can be infected multiple times, meaning even after they've had it and recovered, they can get it again, which means they are not resistant, which means that the number of resistant people should be 0. No one's safe. Nobody's resistant, right? So, unfortunately, that sucks for this town, but for us, it means we can narrow it down to 2 options, right? That's the bright side. All right. They say at time 8, 6708 people are ill with one of the diseases, and 1092 are ill with the other disease. So we have 2 infected groups. Then they say 5,200 other people have been ill and recovered. Now, in the last version of this problem, 5,200 would have represented our R value, but the R value is more representing the number of resistant individuals, not just recovered, but recovered and resistant, right? But in this case, we can't call 5,200 the R value because no one's resistant. They can catch the diseases multiple times. So all we have to do in this case, instead of taking the total minus the, well, I guess we'd still do the same process. Total minus infected minus resistant, but just recognize that resistant will be 0 in this problem, right? So let's take the total. 26,000. We're going to subtract the infected, which is 6708, and the 1092. Again, there's 2 diseases, so there's 2 groups of infected individuals. And then there's the 5,200 have been ill and recovered, but again, no one's resistant, so the number of resistant people is 0. We're subtracting 0. So basically that 5,200 that have been ill and recovered, they're basically like tossed back into the susceptible population, right? So anyway, we'll just calculate this real quick. 26,000 minus 6708 minus 1092, and we get 18,200. That looks like option B, and that checks out. All right, hope that makes sense. Let's keep rolling. I'm going to call this number 12. What is this one? Let's jump into it. They say, suppose a city of 14,190 people is experiencing a viral outbreak. They've calculated the A value, A parameter, right? It takes 24 days to recover. After infection, the person becomes immune. That's great. Day 74, there are 1,947 people infected. 12,101 have recovered, and 142 people are still susceptible. Calculate the rate of change of the infected population at day 74 using the SIR model. So the rate of change, meaning derivative of the infected population, means we want the derivative of the infected population, or I prime. Again, I prime was A times S times I minus B times I. So we need to find A, S, I, and B and plug all those values in to calculate I prime. Let's go ahead and say A is given to us, actually. They say parameter A is 1.58 times 10 to the negative 5. And then B, they tell us it takes 24 days to recover. And we said before that B is found by doing 1 divided by the number of days it takes to recover. Is that a nice decimal? Am I dumb? Let me try that again. It's not a great decimal, so I'm going to just call it 1 over 24. And then S is the number of susceptible. I think they tell us that. They say 142 people are still susceptible. So we'll just call that 142. And we'll go down the line, do infected. They say there are 1947 people infected. And then I don't think we have to use the recovered value at all. I think it's negligible information there. All right. We're going to use Excel. Plug these bad boys into this equation. Alright, so we're calling this I prime. We're just going to plug in these values that we see here into this differential equation. Starting with A, we're going to do equals A, which is, I'm going to use parentheses for this, 1.58 times 10 to the negative 5. You can really just type it in like that. And then we'll do times S, which is 142, times I, which is 1947, minus B, we're going to use parentheses, but we'll just type it in as is, 1 over 24. And then times I, which is 1947. Here's another look at everything we just typed in. Again, this is I prime right here. We hit enter, and we get about negative 76, about negative 77. If we round up, that's looking like option B. And that's all there is to it. Hope that makes sense. Let's keep going through it. Let's bring this back. All right. We got, I think this is the last one I wanted to do. So we're pretty right on schedule here. Wanted to end right about at an hour. So this was 12, this is 13. Thanks so much for watching this, if you're watching. Again, if you want to see more weekly review sessions before your quizzes like this one, I encourage you to hit the join button and join the weekly study sessions option, because this is the only free one. We're going to be doing members only from here on out. All right, let's jump into this last problem. And also, for the future sessions, this will more be a place where you can send problems like that you're having trouble with, and I will work them out like during these sessions. It's meant to like really be almost like an office hours, like a study session kind of thing. Yeah. All right. Let's jump into it. They say, use the table to determine if Q is modeled well by this equation, and if it is, find K. Okay. So the approach here is this. We are given the T values that correspond to Q values. It's very similar to like being given X and Y values, right? Oh gosh. And what we also need to find is some estimated Q prime values. We need to estimate what Q prime is using, using these given T and Q values. So here's how we'll do that. To estimate, I'm going to kind of do it how I've done it in videos in the past. In order to estimate Q prime values at 4 and at 5, I'm going to use the values. let me back up a little bit. In order to estimate Q prime at time 4, I'm going to find the slope between these two ordered pairs. I'm going to find the slope between T equals 4 and T equals 5. To find the slope, we are basically doing y2 minus y1 over x2 minus x1, where in this case, again, the Q values are like the Y values and the T values are like the X values. So let's demonstrate it for the first one. Again, this is to find the Q prime value at 4. We are going to use this pair here. So the y2 is the 30.8151. We're going to subtract the y1, which is the Q value of 42.0762, dividing that by the difference in X values, 5 minus 4. We're going to go ahead and do that for the next pair of values too, next ordered pairs. So in order to find the Q prime value at 5, we're going to use these two pairs, right? So we're going to do y2, so 23.6346 minus the 30.8151, and we're dividing that by 6 minus 5, the change in T or X values. I'm going to go ahead and calculate both these. I'll go ahead and do that in Excel. So so we can work it out together. So I'm going to say q prime at 4 and q prime not at 5, or not at 4. We'll do q prime at 5 for that one. All right, so for this top one, I'm just going to use this calculation here. So in big parentheses, we have 30.8151 minus 42.0762. And we're dividing that, by 5 minus 4, which is, 1. You get it. Let's go ahead and find q prime at 5, which again is this calculation here. So equals, big parentheses, 23.6346 minus 30.8151. And we're dividing that again by 1, or 6 minus 5. And we get this. Again, these are not necessarily your k values, they're just your q prime value. So in our little chart here, we are about halfway done with this problem. This is the important stuff we've just done. So q prime at 4, we're calling that negative 11.261. And then at 5, negative 7.18. I'll go 0.5. All right. Now, what do we want to know? We want to know if this equation basically stays consistent for different t values in this chart. So what I mean by that is we're going to plug in the q and q prime values into this equation here. And we're going to see if when we solve for k, do we get two k values that are equal to one another. So hopefully it'll make more sense as we work through it. For the first step here, using this first column at time 4, we're going to plug in q and q prime into the given equation. So let's demonstrate it. Q prime is on the left side here. We have negative 11.261. It's equal to negative k. K we do not know, but we do know q is 42.0762, and we're subtracting 11 from that. We're going to solve this for k. Okay, so let's go ahead and subtract 11 from this here. From 42, that should be 31.0762. We have negative 11.261. We can go ahead and say if this is negative and that's negative, let's divide by a negative 1 to get both sides positive. And then we're going to divide by the 31.0762. Let's do that over here, I guess. Oh gosh, went too far there. Am I frozen? Oh, good night, I hope not. Has my video been frozen for that long? Oh, don't tell me. Don't tell me. Oh, I hope not. Oh well. Well, too bad no one told me. Man, I really hope that hasn't been frozen that long. Okay, whatever. Let's keep working through it. Sometimes you gotta roll with the punches. Alright, we're doing 11.261. Dividing by 31.0762. We get about 0.36 for that k value there. So we get k is about 0.3623. So I'll just say 2. Oh, I really hope you can see what I'm doing though. Yeah, it looks like that's still moving. Okay. My camera's just frozen though. That sucks. Okay. Oh well. Alright, so we have k. That was just for the first column, the time 4, right? So now we're going to do this second column here at time 5. We're going to repeat the process. We're going to plug in the q and the q prime values into the equation. And the goal is to solve for k in that version too, and then see if these two k values match up. So we're going to do q prime, which, again, the second column, we have negative 7.1805 equals negative k, which we do not know. We'll have q minus 11. So q is 30.8151. And we're going to solve for k. Again, we can subtract the 11 from the 30. That should give us 19.8151. We have the negative 7.1805. They're both negative on both sides, so we can just cancel out the negatives. And again, we divide by 19.8151 to get k by itself. So in Excel, we will do 7.1805 divided by 19.8151. And we get, pretty identical values here for k. And that's a good sign. What that means is the model is consistent. How do they word it? They say Q is modeled well. That's what this means by this equation, right? So Q is modeled well by this equation means that we solve for Q here, and we solve for Q here, solve for K, and these K values were pretty identical. And those K values were both 0.36. All right, I hope that makes sense. I'm going to call it here. Thanks so much for watching. I'm going to scroll through these so you can get a glimpse at everything we did for each of these problems. I'm going to start from the top, actually. Again, if you want to see review sessions like this each week, hopefully where my video does not freeze. I still don't know what it's doing. Hopefully that wasn't a long time ago. I think you can still hear me. Yeah, check, yeah. All right. If you want to see videos like this, review sessions like this each week, go ahead and join my weekly study sessions option by hitting the join button. All right. And again, if you have any questions on any of these quizzes or practice problems you're working on, go ahead and send them my way, or just, comment on the YouTube videos, whatever. If you want, you can always email me at carterdmath@gmail.com. I'll write my email out in just a minute. Or I'll just do it now. That'd be ignorant. Just make you wait. So it's Carter, DEEE, math @gmail.com. All right, a little sloppy, but you get it. I'll go through the rest of these, and I'm going to call it a day. Again, going forward, when these are members-only sessions, I encourage you to send me problems that you're having trouble with, and I can work them out during these live sessions. These live members-only sessions. All right. Let's get a full view of that one. All right. Alrighty, I hope everyone has a great day. I'll see y'all later. Bye-bye.